Lang's pathway. In some regions there will be turbulence, in some regions there will be laminar. And also, like let's say, if you look at coughing or sneezing, generally like the initial form is like at quite a high velocity, and the whole droplets come as a form of like they refer as turbulent clouds. So it is important to know little bit of turbulence also. We'll do briefly like the Reynolds number using the RANS method. Before that, let's just discuss briefly the Reynolds number, which you all know. So the Reynolds number is like the inertial force by the viscous force, and then like let's say if we define the inertial force rho L cube, we take the acceleration, the convective term. We can also write the v by t, but that will again we can convert it to the in terms of L by u. So v dv dx, let's say, so we can write u square by L here, and then or like if you write like this v by t, we can say like u t, we can again write like this. It eventually becomes u square by L. Then viscous force, take the viscosity, the area is L square, and let's say del u del y, you can take as u by L. So then it becomes first, let's say rho L square u square, here also mu into ul. So eventually we achieve the final form which we are usually accustomed to. Then it can also be interpreted as like the viscous time scale by the inertial time scale. So from this definition we can say that when Reynolds number is high, inertial force is much more dominant compared to the viscous force. In this definition, first let's define the viscous time scale is L square by nu. So you can see here it is dimensionally constant, like consistent. This is meter square, let's say in SI system. Nu is meter square per second. So ultimately L square by u term will give a unit of second. The integral time scale, inertial time scale, we can say simply as L by u. So thereby we can rearrange as ul by nu. So we can say that when Reynolds number is very high, the viscous time scale is much higher compared to the inertial time scale. So this, like one can be interpreted in terms of force, one can be interpreted in terms of the two time scales. So in context of just like since I am like also teaching the convective heat transfer, there is a non-dimensional quantity called Becquerel number, which we generally say like the diffuser time scale by the inertial time scale. So when it is like thermal diffusion, we write as L square by alpha. Alpha is the thermal diffusivity, and inertial time scale is the typical L by T. So this eventually becomes UL by alpha. In the chemical engineering context, many times this alpha instead of the thermal diffusion coefficient, we go by the mass diffusion D. So then it becomes UD by, sorry, this is UL by D, more like a diffusion coefficient. So these are the like the two time scale definition. So let's say that like when we like focus on the audio is okay. So when we refer to the turbulent flow, first we say that like the Reynolds number is obviously very high, so quite high. Then generally we say that the flow is chaotic. Again, like the chaotic aspect requires much more discussion. We are skipping for the time being. What we say that like let's say in a turbulent flow, if there is slight variation in the initial conditions, it will lead to different trajectories. Like let's say here we take at a single point, there are certain variations in the initial conditions. One flow trajectory will be like this, another trajectory may be like initially close to each other, but it will land at some other place. Okay. Then we say, like always we say that if we look at the velocity, it is always fluctuating or like random and fluctuating. So, like let's say Reynolds studied everything qualitatively. Later, with hardware anemometry, or like much later when people studied like PIV, they saw like let's say like with a device which measures signal in the laminar flow, it looks like a straight line. The velocity signal, okay, or like very small, like these sort of small oscillations. These fluctuating components are in the range of the least count of the instrument. Okay, very like smooth signal. Whereas, like let's say at a single location, if the flow is turbulent, the velocity is like quite. We have a mean component, but it is fluctuating about the mean component. So if we look at the absolute magnitude of the velocity for like let's say at a given Reynolds number, let's say a pipe flow Reynolds number around 10,000. Okay. So then like in each different measurement, here is one signal, the other signal will not exactly match with each other. So it will what will have like some sort of other kind of signal will come. So each measurement will produce unique sort of velocity. But like what Reynolds proposed, that in this kind of scenario, since we are not like getting, like we can't predict the exact this kind of behavior, what we should do, we should focus on the mean quantity and then like subtract the mean quantity from the actual quantity. So let's say if at a given location we can like decompose this as the mean component and the fluctuating component. So this is mean component u bar and u dash is the fluctuating. And then he says that like let's say at the Reynolds number 10 to the power 4, even if the two velocity signals are not matching with each other, it is highly likely that the mean component will be same. And also if we take a statistics of the fluctuating component, that will be similar to each other. Although the individual components may not like be overlapping with each other. So, like let's say, how do we do the mean? One is like the time averaging. So, at a given location, let's say u bar x or x0, like x0 implies the three coordinates. You can say, like let's say, if we measure the velocity for a given amount of time, capital T, if we starting from T1 to T2, whereas like T2 minus T1 equal to T, and let's say that U is measured at this location and for time T dt. So this is the time averaging procedure. So in this context, like just a funny story, in the IT Roper faculty interview, someone asked like what do you mean by the time averaging of this quantity. So I simply wrote like from 0 to T or 0 to capital T 1 by T UX0 comma T dt. So one professor was not happy with the definition. He didn't like the idea of assigning the lower integration limit to 0. He said that let's not keep it 0, rather like write T1 and T2. So it's a matter of definition. Just if we write from T1 to T2, just remember that the difference of the two times is the capital T. Okay. Or otherwise we can start from 0, write capital T here, and then we divide by the capital T. So, like you can see that this is like u equal to u bar plus u dash. If we take the mean of the two quantities both the sides, like taking mean of both sides, what we do, let's say this over bar represents taking mean, so u bar plus u dash, we write like this, then this quantity is already mean, so definitely like taking mean of a constant quantity will give the same term, so u bar plus u dash bar. Now you can see these two terms are equal to each other. So essentially, by definition, the mean of the fluctuating quantity, that will be 0. So this property will be always used while we like derive the RANS equations. So let me just write here one part. So any fluctuating quantity, let's say u dash or p dash w dash, the mean of this fluctuating quantity, or let's say for the pressure component, if we write the fluctuating pressure, by definition, the mean of these fluctuating components are 0. So then, just like time averaging, there are two other types of averaging, which are called space averaging and ensemble averaging, or some people pronounce it in the French way, but in the French pronunciation ensemble or something like that. So anyway, space averaging is basically like, let's say at a single time we are measuring over a 2D or 3D field at a single instant. So here like you at a given time instant t1, let's say, and the area or the volume whatever we are, like let's say for the sake of generality, we divide by the total volume, then like let's say over the whole field, so like you can write the three coordinates and at a single time instant into like let's say dx dy dz. So basically let's say like for the sake of simplicity, we take a 2D planar field, we measure at 10 different locations at a single time instant, and then we take the average of these 10 points, and then we say that like what is the space average quantity. So that space average basically gives an idea that whether the velocity is homogeneous or what is the like the degree of variation in the whole flow field. That sort of space average. Then the ensemble averaging, so that basically, like let's say we have a very easy experiment to do. We carry out the, let's say some pipe flow experiment, I equal to 10 to the power 4 just for example here, and then over the cross section we are doing some sort of PIV measurement and we are carrying it out 10 times, or some other easy experiments we are carrying it out 100 times. So then like for the single location we are having 100 measurements and then we do the averaging procedure. That will be the ensemble averaging. For our RANS derivations, we will be sticking to the time average like the time average method. And also one thing, like, so these are the like for the RANS simulation, we will be sticking to the time averaging procedure. Just right. So RANS is Reynolds averaged Navier-Stokes equation. So I am just writing down the first two ones, the Navier-Stokes is obvious. So Reynolds averaged. Okay. So here one thing, like there is some term called stationary turbulence. By stationary turbulence means, like let's say we take this mean component, when it is stationary turbulence, the mean quantity is not changing over time. So let's say some sort of signal is like this. If we take the mean of this quantity, so let's say this is U versus T, then the mean quantity is not changing. But let's say some sort of pulsatory flow or some whatever, like some time average, but the mean component is changing. So let's say some sort of the mean is changing like this and the velocity signal is some sort of fluctuating about this mean quantity. So here it is clear that when you are calculating U versus T and plotting, if we plot the mean quantity, this curved line represents the mean component. Okay. So in this case, the mean component is changing. So then, like let's say for the stationary turbulence, when we are writing the time derivative term, if we assume the stationary turbulence, this we can take as 0. But for non-stationary one, since this mean quantity is changing, this can't be, this is not equal to 0. So these are the like two definitions which will be adopted. So if we assume that the turbulence is stationary, we can neglect the mean quantity also. Otherwise, for non-stationary turbulence where the mean component is also fluctuating, we can we have to consider the time derivative term. Okay. Okay, so we said initially that any quantity you can write like U bar plus U dash, same goes with the other quantities. So let's start with the continuity equation. Like you know that here again we are using incompressible flow. So for incompressible flow, we can simply take the divergence of the velocity field is equal to 0. So let's say divergence of velocity field is equal to 0. Following that, if we write down the index notation like del u I, del xi or del u j, del x t equal to 0. Following that, let's write down first like del u, del x. We will just using two components, but like you keep in mind that in general it is like three components, del u x, del u y equal to 0. Now, let's say we are assuming turbulent flow. So, essentially, you can write like this u bar plus u dash plus del del y v bar plus v dash equal to 0. Again, if we carry out the averaging procedure, let's say we carry out the averaging procedure here, the next step it will come del del x u bar plus del del y v bar equal to 0. So this shows that the mean components are following the continuity equation. Okay. So let's say if this is equation 1 and if this is equation 2, then if we just simply subtract the equation 2 from the general equation 1, we can also show that del u dash del x plus del b dash del y is equal to 0. So this shows that, so this equation 3 is essentially, here you can see that we are starting with the general continuity equation for 2D flows. Then we are doing the averaging procedure. We are showing that the mean components are following the continuity equation, and after that we subtract the mean equation from the first one, and we are showing that the fluctuating components are also following the continuity equation. Okay. So this part I keep it intact. We can write the momentum equation in the other half. So we start with the x equation, like let's say the x momentum equation will start with the like this rho del del t plus del del x u square. You can write u dot grad u, but I will just carry out the averaging procedure. For this purpose, I am writing like this: del del y u v plus del del z u w. So this is the LHS part, the left hand side part. Then we can write equal to minus del v del x and plus we already know that mu of Laplacian square u, but then again, like we will write this term now in terms of the shear stress. So let's say for the, let's just recalculate the stress tensor. You can hear, right? आपको सुनाई दे रहा है? Okay. So let's say tau xx, tau xy, tau xz. We follow this column only, tau yx now, tau zx. So if you remember the stress tensor, we know that along this column, like let's say tau ij, when I am saying in terms of the index notation, I is the area vector direction, right? And j is the actually the stress direction. So let's say if the area vector in this case is acting in the positive x direction, so here, like let's say sigma xx represents that the area vector is in the x direction and it is also as well acting in the x direction here. Now let's say this is x, this is y and this is z. So you can see vertically the stress component, its area vector, if we write like tau, the area vector is will be, the first index will be always x, right? And since it is acting in the z direction, you can write like tau xz. Following that, like perpendicular to the board, this is or rather if we like draw like this will be tau yz. On the other hand, so basically the rho wise component represents the stress having all the area vectors common, right? That is in the x direction. Well, sorry, this should be tau xy, right? So x is the area vector and y is the direction. So the column wise stress components basically represents the stress components acting in the x direction. But please note the first index are different for the cases. For the x momentum, it will be the first column, that is tau xx, tau yx. Basically, this area vector is acting in the y direction, but this component is acting in the x direction. Okay, so let's just see here. You can write this as the right hand side term equal to minus del t del x. Again, here we are intentionally dropping the body force term, because body force will be not fluctuating. So that is the assumption. So you can write del del x tau xx plus del del y tau yx plus del del z tau zx. Okay. Here you can see that if we carry out the averaging procedure, the del p del x term you can write, you can see from that side this board, right? It's not a problem. So at least the del p del x, if we carry out the averaging term, that is the easiest one. So P is P bar plus P dash. So when you are writing like this, so essentially if we write like this, it becomes only del P bar del X. This term, the del X of P dash, this is 0, so this is dropping out. Similarly, here the viscous terms mu grad square Q, if we carry out the averaging procedure, this becomes mu grad square U bar only. The fluctuating component dies out. So the stress components again, like this, when we carry out the averaging procedure, we'll simply write like this, tau xx bar. Okay. So this means, like let's say tau xx, if we write the general term, here p is already exclusively written. So minus p plus let's say 2 mu del u del x. Okay. So when we carry out the, let's say for the time being, since we have already exclusively written the p term, if we carry out the averaging procedure, this becomes 2 mu del u bar del x. Okay. So then, like when we are carrying out the right hand side term averaging, here we are writing equal to minus del u bar del x plus del x. So this now just involves the derivative terms involving the mean velocity component plus the del y tau yx bar plus del z tau zx bar. So just for the, like if you recall here, you can write down the index term and you can also expand the, so let's say tau ij equal to minus p delta ij plus 2 mu Sij is the velocity gradient terms. So Sij, so please note here I haven't like wrote the lambda term because we are assuming that it is incompressible. So this is half del ui del xj plus del uj del xi. So when we are writing the tau xy term, this is conical delta, this anyway will cancel out. So you can write 2 mu half of, like let's say x is 1 and y is 2. So you can write del u by del y, right, plus del v by del x. So this becomes mu del u del y plus del v del x term. Similarly, if you expand the tau zx term, this will be tau zx term equal to mu del u del z plus del w by del x. Later when we, if we simplify, you can see that some of the terms will cancel out by using the divergence of velocity term equal to 0, and essentially when we expand all the terms, we will be getting the Laplacian of mu grad square u. Okay. Similarly, when in the y direction momentum equation, we will be landing up with the Laplacian of mu, like mu Laplacian of v and mu Laplacian of w. So here, so let me just write down maybe the y momentum equation. We know that there will be mu grad square v and mu grad square w, but this essentially comes from this sort of derivatives. So here, let me just write it anyway. First, here you can see that tau xy, this will be like tau yy and tau z1. So in the y direction it will be del del x tau xy plus del del y tau yy plus del del z tau z1. So here also you can see that if you note the second index, all are y, but the first index, they are acting in, the area vectors are acting in the different directions, that is x, y and z. Similarly, in the z axis you can see the component, the second index will be always same, tau xz, this one will be tau yz and this one will be tau zz. So if we like follow this pattern, we can write this is varying along the x, this is varying along y, and this is varying along z. So again, the right hand side stress components for the z direction, the simplified term we have already written mu, that's Laplacian of w, but when we write down like this del del x, this will be del del x of tau xz plus del del y of tau yz plus the del del z term of tau zz. Okay. So in this way, like when we do the actual derivation starting from, let's say, simple like this sort of cubic fluid element, we take into account the stress components in this way. First we write down the derivatives of the stress components, and then we, like for incompressible flow, we simplify to the Laplacian of the individual u or v or w. So let's write down first here. Let me just write down the x equation. So let me just write down the single row. W equal to minus del del x plus del del x term, which is tau xx plus del del y tau yx plus del del z tau zx. And here, if we assume here the stationary turbulence, when we carry out the averaging procedure, that will be 0. If we don't want to negate this term, we assume, like for a general case, we can write here this term. After averaging, you can write dv by dt. So just keep in mind the subtle definition of the stationary turbulence concept. Means ideally, like turbulence is always fluctuating. This stationary turbulence, it deals with the mean component. Okay. So now we'll just take account of the one of these convective terms. So let's say u square, this becomes u bar plus u dash and u bar plus u dash. We write down this term also. This is u bar plus u dash, v bar plus v dash. So you can see we just simply write down u bar square plus u bar u dash. This we multiply now. Let's write down like this: u dash by u dash into u bar plus u dash square. Now we do the averaging procedure. Let's write down like this. First, carry out the mean of all these quantities. Following that, this is a constant quantity. This will be as it is. Now, the u bar, u dash bar, when we carry out like this becomes like this into u dash And by definition, we know the mean of this fluctuating quantity is 0. So this becomes 0 here. So you can see here that this term and this term are essentially same. So both these quantities are 0 plus 0 plus 0. But we have said that mean of the fluctuating component is 0. But this is a positive quantity, right? The mean may be, let's say, like if this is the mean component u bar, in this part it has the fluctuating component u dash, it will be negative, here it is positive. But when you are carrying out the square term, it is always giving a positive quantity, and this is always in non-zero part. Okay, so u bar square plus u dash square. Likewise, if we carry out the averaging procedure of this one, we can write here that u dash p dash, or we can write it together also. This implies that u v mean of the product of the mean of the product of the mean components u v, or rather write like this to avoid any confusion. U dash v dash is like a non-zero quantity. So this has been, here it is easy to prove the u dash square or v dash square or w dash square. This will be always non-zero. What about the mean of the two different components? So this is like little bit some sort of, we take a simplistic scenario and we show, later we will just show that it is always like a positive quantity when we define the Reynolds stress term. For the time being, just think that product of this product of these fluctuating components are non-zero. We can't rule out them. So u dash v dash. Likewise, the third term will also be the u plus u bar, u bar plus u dash, w bar plus w dash. When you carry out the averaging procedure, this will become u bar w bar plus u dash w dash mean. Okay. So one point, like when the mean component is multiplied with the fluctuating component, and then we take it, then we are taking the averaging procedure, this will become 0. But when the individual fluctuating components are multiplied with each other, then when we are taking the mean, it is a non-zero quantity. So therefore, you can see u dash square, mean of the u dash square, mean of u dash v dash, and mean of u dash w dash, those will come into picture. So let's write down the left hand side average quantities here. So this term will give these two terms. One is the square of the mean component, and one is the mean of the squared fluctuating component. Likewise here, del y, this becomes uv, and I can write like this, del z, del y, u dash v dash here, and this one is del z, w, or w like this in this way, u dash w dash. And these ones like minus del p bar del x plus I am not writing the three components, just writing one component. The two components will be written like same way, del x tau x in this way, right? The other two components also will write in this. Okay, so now you have seen that these three terms are generating six components. Huh? Which one you can come by this time? The first time free. Use all those just by the oh, acha, acha. So let's, for the sake of, we make it station turbulence. Okay, let's remove it. So here, like we are assuming stationary turbulence, so that's why we are dropping the term, and then we are just left with the three terms, and these three terms, after erasing, are generating the six terms. So what we do are seeing now, like normally these components are taken in this part, and they are said that these are Reynolds stress terms. But actually, if you see the derivation, these terms are arising. So essentially, how are these terms coming? This, when we are like doing the momentum equation derivation, this is basically the variation of the momentum flux in the different directions, right? So you can imagine that this is the variation of the momentum flux due to the mean component, and this is the variation of the momentum flux due to the fluctuating component. Although normally, like in the when we like don't look at the derivation part, we straight away say that these components will come into this side, and we term those as Reynolds stress. Okay, but the physical significance is, please remember, is not stress actually, is arising due to the whole fluctuating component. Later we will club together in terms of the stress component. So here, like after this, let's write down, like we are dropping the stationary term. So on this side, if we write the derivative term, we can also drop as like depending upon the choice. I will just keep it because I like later want to show that it can be clubbed together. So let's say we are writing like this: del x u bar square plus del y u bar v bar plus del z u bar w bar. And on the other side, we are writing minus del v bar del x plus del x tau xx minus, so you can see we'll take this component, sorry, here is there any color chalk, then it will be easier. आप कोई कलर चौक दिख रहा है? सभी व्हाइट. Okay, so here you can see that these are the fluctuating components. This again, this is one, and this is one. So these will take on the other side. Now we are writing like this: minus rho u dash square plus del y tau yx minus rho u dash v dash plus del z tau zx minus rho u dash w dash. Okay, so now you can see after the emerging procedure, we are taking the fluctuating components in the this side and we are clubbing it with this one. Okay, so please see, this is again over bar. So the tau over bar xx essentially means 2 mu del u bar del x. Tau yx means del u bar del y plus del v bar del x. So even if I forget to remember, like write the overbar symbol, please assume that this is Everest quantity. Okay. So how much time? I guess I have still less time, some 15 minutes time. So now you can see that this one and eventually these four terms, let's just write here T here. So this can be further simplified as del bar del T. The left hand side terms, if you carry out the averaging procedure and following using the information flow conditions, you can finally write the left hand side as like this. Okay. The pressure components will be always minus del P bar del X minus del P bar del Y minus del P bar del Z. If we consider the body force, we are saying that the body force is not fluctuating. So, for the sake of convenience, we are just dropping those terms. And even if there is any body force term, that will be not like having any mean or fluctuating component. The gravitational force will be always as it is, or electromagnetic force will never fluctuate. And even if it fluctuates, like Coulomb is doing some electromagnetic force, that is not like this typical turbulent fluctuating quantities. Okay, so these are this one is essentially the left hand side, this is the pressure gradient term. If we now look at the stress components, so let's just write down the stress component here. We just derive the left hand side, sorry, the x momentum equation. The stress component will be tau xx minus rho u dash square plus del y tau yx bar minus rho u dash v dash plus del z tau zx minus rho u dash w dash. So now you can see here there is u dash square, u dash v dash and u dash w dash. If we club all the three like directions, first write down. So this is the x momentum. If we do the averaging procedure of the y momentum, we have earlier written down the stress components. So here again, just remember that the y direction components are tau xy, tau yy and tau zy. It is varying along x, it is varying along y and it is varying along z. So when we carry out the averaging procedure here, we are writing del x tau xy minus here now it will be, or let me just write down the Reynolds stress in matrix form first, that will be easier. So normally we write, let's say, rho ui dash uj dash. If we expand this in the matrix form, like let's say minus of rho, this will be u dash square, this will be u dash v dash, this will be u dash w dash. Okay. Now here this component will be u dash v dash, this will be v dash square and this will be v dash w dash. And here it is u dash w dash, it is v dash w dash here and w dash square. So one thing you can see that if we follow the actual stress component convention, we can say that when we are using the x momentum, this column is used. When we are using the second one, y, the second column will be used. So then you can see if you follow the Reynolds stress matrix, the second component, if we look here, you can write here U dash V dash. Then del y, this is bar again. We know this will be yy minus the rho. Which component? This component should come, right? V dash square. So here rho V dash square term is coming plus the del z tau zy bar minus rho w dash square. Now follow this logic and try to derive the z momentum equation and tell me, or one of you can come and write down. So see, look. Rho, sorry. So this should be rho w dash v dash, right? So maybe it's okay, right?
Yeah.
So no, for the z momentum. So z momentum involves, let me just write down the stress components for you. So this will be tau xz, tau yz, and tau zz. Okay, and these are the Reynolds stress components in the z direction. So Shasikant will try to just write down the stress components in the z direction following this one. U dash W dash. Okay. So this is correct, right? What is here written. So you get the logic. Like initially, instead of writing the mu Laplacian of u, we have written the direct stress component so that we can just club these quantities together with the x terms. And that's kind of like after doing this algebraic operation, since it is clubbed with the stress component, that's why we call it Reynolds stress. Although we just said that physically it implies the momentum flux due to the fluctuating components. So please keep in mind about the physical significance. Okay, so now if you look here, this is the matrix here. So you can see that these two are equivalent, these two are equivalent, these two are equivalent. So here it's a symmetric one, right? So this is symmetric and 6 unique or individual components have come. So earlier, like let's say for a simple laminar case, we are using the 3 momentum equations and the continuity equation. So u, v, w and t, these are the unknown terms. We can find out from 4 different equations, 4 different variables. Here we are using the 4 different equations, the continuity equation and the 3 average momentum equation. But then we have no clue about these 6 individual components. The averaging procedure is generating 6 unique components, so that's why like the number of variables are more than the governing equations. So that is like, let's say, since we do not know anything about these average quantities, if we further carry out the averaging procedure, in the next step what you will see like some sort of rho ddt, like let's say uy uj dash average quantity, this will be generating some equation which will be ui, uj, uk dash. So this will be now triple product of three fluctuating components. This again it will be three like more number of equations. So like if we further carry out this one, this will involve some equation which will generate ui dash, j dash, k dash, and u k dash. So it's a never-ending problem, right? So this problem in turbulence is called the turbulence closure problem. So that is why, like, we do some approximations. So there is not too much time. I just want to stop here, and we'll like continue this part in the next class later. We'll like discuss the schedule later. And so that's all for now. We carried out the leveraging procedure, and then we showed that these are actually not stress components. And due to the leveraging procedure, analytically if we try to solve, this will not be like this will not make our life easier, and that's why since the number of variables will always be more than the number of governing equations, we say it is a turbulence closure problem. Later, how to deal with turbulence closure problem in the next session we discuss that. Okay. So let's go to the mechanical seminar and we'll start at 12. The